In this video, we'll cover average reaction rates. Say that this is you right here, and you are about to talk to all these different people under 1 hour. Let's see how many people you're able to talk to under 1 hour. 1, 2, 3, 4, 5, 6, 7. So if I were to ask you, how many people were you able to talk to under 1 hour? You would say 7 people per hour. That's the rate in which you were able to talk to under 1 hour. Why is this related to chemistry? Well, in chemical world, you have reaction rate as well. How much product can be formed under a period of time. Take, for example, nitric dioxide forming into nitric monoxide and oxygen gas. Well, nitric dioxide, if you look on the left, is going to form into nitric monoxide. So here is my nitric dioxide forming into nitric monoxide and oxygen, highlighted in blue and red, respectively. And you see another one. Here's another nitric oxide forming into nitric monoxide and oxygen gas. Now, all of this reaction takes time. And notice the concentration of the NO2 is diminishing as the concentration of NO and oxygen is increasing. So the average reaction rate, we can define that as the change in concentration of the reactant or the product per unit of time. In simplicity's sake, we would write this in its unit would be molarity over time, and that time would be second in particular. Let's focus a lot more on the reactant. How do we find the reaction rate of disappearance of NO2 over time? If you look at this graph here, this is a graph of the reaction of NO2 in green. The green, you'll notice that the concentration is diminishing as time passes. If you look at this box over here, you see the value of the NO2 decreasing over time. The increments here shows in 50, 100, and 150, 200. And you'll notice that a product side, it is increasing because that is forming as time passes. But we still haven't figured out an actual value for the reactant, right? What is the rate? What is the average rate over a certain period of time? In order to find out the actual number, you'll need to have an equation. And that equation would be the change in concentration of NO2 over the change in time. Or if I were to expand it out, which is shown on top, it's the concentration of the final minus the initial all over the final time minus the initial time of, it's not necessarily the beginning and the end, but from the frame that you're looking at. For example, here's the average rate. What is the average rate at which concentration of NO2 changes over the first 50 seconds? So if it's the first 50 seconds, my T2 would be the 50 seconds because that's where it went to. My initial time would be 0 second because that's the very beginning. So my concentration of NO2 at T2, or where it ended, as shown here at 50 seconds, is 0.0079 molarity. So 0.0079 molarity, whereas initially it was 0.0100 molarity. Now that we have all these values, you're going to go ahead and plug them in onto this expanded form in order to find out the actual value. So let's go ahead and calculate that out. So that would be negative in the front, and on the top, 0.0079 minus the 0.0100 all over 50 seconds minus the 0 seconds. So let's go ahead and punch this into the calculator. 0.0079 0.0110. And then we'll go ahead and press enter. That's going to give me a negative value, but don't worry. And then we're going to divide that by 50 minus 0. 50 minus the 0. And then press enter. And then you'll see that negative sign in the front, which means I need to multiply that by -1. And I get a positive 4.2 times 10 to the -5. And the units are molarity per second. Okay. So that's how much, that is the rate in which this molecule is diminishing, the NO2 molecule is diminishing per second. Now let's look at in terms of the product. If I were to look at in terms of the product, I'm looking at either the nitric oxide or the oxygen gas. I'm going to go ahead and target nitric oxide. So for the average rate for the product, it looks very much similar to the average reaction rate of the reactant, except for that it doesn't have a negative value in the front. If I were to do an example of this, it shows that what is the average rate in which the concentration of the nitric monoxide changes over the first 50 seconds. Again, my T2 would be 50. My T1 would be 0 seconds. My ending concentration at T2, it shows 0.0021. Molarity, and then NO at T1, it didn't have any, so that's 0 molarity. So go ahead and try putting these values into here and see what you get. So coming back, you should have gotten the same value, which is 4.2 times 10 to the -5 molarity over second. What do you know? The reducing of the NO2 diminishing rate is equal to the increasing product forming. The rate is exactly the same. And that's because it is 2:2 or 1:1 ratio. If it's 2:1, the value for oxygen definitely would be different. Let's do a learning check based on what we have learned so far. What is the average rate? Okay, we're looking at the average reaction rate again, at which the concentration of NO2 changes from 200 to 250 seconds. So you're going to try this on your own and come back and check the key. And here is the key. If you got a negative number, you might have forgotten the negative value or the -1 value that's in front of the reaction rate for the reactant. Remember, looking for a reactant, you have to have a negative value in the front. You can never have a negative reaction rate. Let's go on to another learning check. Might be a little bit challenging, but I think we can do it. The average rate of disappearance of ozone in the reaction, in which the 2 ozone forming into 3 oxygen gas, is found to be 9.0 times 10 to the -3 over a certain interval period of time. And then that's in seconds. What is the rate of appearance of O2 in this interval? So it's not giving you much information, or so you think. So we know that the average rate for the product, average rate for the product would be 9.0. So my product, average rate of O3, ozone disappearance. So the reactant disappearance is 9.0 times 10 to the -3 molarity per second, right? Well, we don't know much, but we do know that there is a coefficient in front of the reactant and the product. If you want to know the average rate of the product that is being formed, which is the O2, we take the coefficient of the product on top, we take the coefficient on the reactant on the bottom, so it's 3/2, and multiply by the reaction of the product. Oh, of the reactant, I'm sorry. So if you were to calculate this out, let's go ahead and punch this in. Calculate this out. We're going to write 3/2, multiply, and then I'm going to put those two in the parentheses to let them know those are one entity. And then that's 9.0 times 10 to the -3 go ahead and press enter, and I get 0.0135. So maybe 0.014. Molarity per second. So that is the average rate of the oxygen that is being formed over time. So if I were to overview this, okay, so if I have an overview, say you have A, big A, plus little b, big B, forming into little c, big C, plus little d, big D. So what that means is these guys are my coefficients, right? These are my coefficients, just like the number of these 3 and the 2. And the A, the big letter A, B, C, D represents the reaction chemical in itself. And you know what then I'm asking for, what is the rate, the average rate of, say, C. Okay, I want to know C. Then you would take the coefficient of what you're looking for, which is the little c, and whatever the coefficient of the reactant that you already have value of. So say you have reaction value of A, so I would put A on the bottom, and you would write the reaction, you will multiply by reaction rate of A here, okay? What if you want to know the average rate of B, okay? And you know the average rate of D, okay? Then you would write the coefficient of what you want on top, and you write the coefficient of what you already have on the bottom, and the reaction rate of D based on what you know so far. So always the coefficient of what you're looking for, it goes on the numerator. The coefficient from the rate that you already have goes on the bottom. Then the reaction rate in itself should give you the value.